So hello again. Tonight we're going to talk about that asteroid that has been in the news lately of potentially encountering the Earth in 2028 or 2032. What it's all about, what kind of defensive mechanisms might make sense. So recently, the percentage of potential for the asteroid, which is 2024 YR4 that they found in late 2024, that would impact potentially in 2032, but we won't know much more for sure until maybe 2028 because it has a 4-year orbit. But I've been seeing way too much fear, uncertainty, and doubt, or FUD, being injected into the common public that nobody's saying it's going to come and get us. It's going to wipe out the planet. But they're just leaving that hanging out there as it could hit the Earth. It's big. Well, it's nowhere near as big as the thing that wiped out the dinosaurs. But yeah, so I've talked about how to defend the Earth from these sorts of things in the past over the years. And I said, well, they're putting it out there in the public again. I've got my 2 cents worth always at my trusty side. So I'll just get into the mix of things. Maybe some of those folks whose knee-jerk response is, let's nuke it, will think a little more before they try and do something stupid. So when an object out in space, be it an asteroid or a comet, is in an orbit, that orbit may occasionally, after a while, coincide with the orbit of the Earth around the sun. So anytime the orbits coincide, if the Earth might be in that same area of its orbit when this thing comes flying by, that's something that we need to pay attention to. That's an Earth crossing asteroid or comet. You know, if it's just merely crossing before Earth gets there or after Earth goes by, we don't worry too much about it. If there's a low likelihood of impact, you know, it winds up getting between the Earth and the moon, somewhere out there. We don't pay much attention to it because there's a lot of stuff dropping out of space every day, a lot of dust from bolides and such that we don't pay much attention to until they get bigger. But when something is going to pass the Earth, even if it doesn't hit, if it's going to pass the Earth below geostationary orbiting satellites, it could hit a satellite. There's lots of space out there, but it increases the probability that it could hit something. But most of these will self-destruct tens of miles above the surface, although the shock wave, the sonic boom, can do damage on the ground. If you remember from 2013, the Chelyabinsk impact in Russia, the impact itself was very small, sort of smaller than a soccer ball. But the shock wave broke a lot of glass, shattered a lot of window frames, and that injured people. You know, it didn't actually hit buildings and take out buildings. This just shock wave in very old buildings with wood frames and, you know, caulk glass and glass that wasn't tempered. Yeah, it's going to affect that. Or if it's something sufficiently large to make its way through the atmosphere and impact somewhere on Earth, then like this thing, we have to do an analysis and further observations and such. And if it's really big, we could wind up with what is known as an extinction level event or an ELE. And if that's the case, what do we do about it? Because this would be the real world, not a movie. So let's talk about the orbits first. Most of these near Earth things that are orbiting, they're either orbiting the sun or one of the other planets, or they're strays from the asteroid belt or the Kuiper belt or the Oort cloud. And all those different orbits are available for these things to come in close to Earth. But if it's an orbit that carries it to the sun may pull it in and destroy it if we're lucky. If it's going past Jupiter's a big garbage collector from a gravitational standpoint. And if you remember that thing that they were concerned it might hit the Earth and it broke apart into 9 pieces, it was called the Shoemaker-Levy 9. Remember that one? Put big bruises on Jupiter. If any one of those had hit the Earth, it might have been a near extinction level event. But luckily they hit the much larger Jupiter that's mostly gaseous atmosphere and not a problem for us. There's a lot of stuff hitting Jupiter all the time. One has actually hit Jupiter since then, and we actually have pictures of the bruise, so to speak. But these are many megaton scale explosive events that we don't want to have happen here. If something is closer, let's say orbiting one of the inner planets or orbiting the sun near the Earth, then these are called near-Earth objects, or NEOs, to be confused with that guy named Neo. So we have all these orbits, and sometimes the orbits will intersect or interact with one another. An orbit does not need to be in the plane of the solar system. It can be skewed, it can be tilted, it can be rotated. And all of these things become factors in. If we knew the orbit more precisely, then we could have a better understanding of whether or not it's going to hit the Earth, and if so, when. An orbit need not be circular. An orbit can be elongated. And as you get out into the far part of the solar system, the orbits get really elongated and tilted. And so if something's going to come by as it's close to the sun or close to the Earth, that would be, you'd see para, like perigee if it's close to the Earth, perihelion if it's close to the sun, apogee, farther away, apohelion, farthest from the sun. So all these different parameters associated with an orbit, you have to know what the orbit is in order to understand them. Now, once you understand the orbit, it could result in, it comes by every so often and it's not a problem, like Comet Halley. Every 76, 77 years, we know it's going to be coming by. It's interesting to see, and we can count on it. But we know it's not going to hit the Earth. But long doesn't mean forever. There are things out there like Apophis that has a long duration orbit that every time we look at it, we go, is it going to hit us on this path or is it not? So far, it's not. But things can be nudged in their orbit. So if it's, we might see it try and hit us again in another 80 to 100 years. Push the ball down the road. We'll figure that out later. But we're not going to do anything about it in the meantime. Fix it later. Somebody else's problem later. So once you have one of these orbits and you have a definition for it and you know it's not going to hit you, that's not fixed because the orbits can change and you can go from a zero to low probability to an impacting probability. And the way this happens is through things called perturbations. Something perturbs or changes this orbital shape, this orbital formula. The one that you have to watch out for that can sneak up on you is solar wind. There's a wind of particles coming off from the sun. Yes, even at night. And if your asteroid or comet is going through this, it will change its orbit. It will change its velocity. If the solar wind is hitting it face on, it slows it down. If as it's leaving it's leaving the sun, it gets hit from behind, it speeds it up. Not enough per day or hour, but over years, this can push or pull on the orbit. Or it can fly by something. Let's say we've got something that is on an orbit that takes it past the sun periodically. And coincidentally, the planet Mercury just happens to be nearby as one of these orbits goes by. Even though Mercury is a small planet, it has gravity. So its gravity can either push or pull on that comet or asteroid as it goes by. Small amount, but it might be enough to make a difference. Or if something is coming in from the Oort cloud, and this is the first time it's looping around the sun, you have a newly defined orbit, but you won't know until after it goes around the sun. Jupiter, if something's coming in from the outer part of the solar system and it's going to pass Jupiter, Jupiter will definitely have an effect on it, pull it over, or if it's on the other side, it can push it away, accelerate it, or decelerate it. And then what happens if something's coming in from the outer part of the solar system and it happens to actually collide with, let's say, an object in the asteroid belt? Now you've got a billiard scatter activity going on. And you have to plot the new orbits of all those things. Now, when one of these changes, one of these perturbations occur, you can have a change in velocity or direction, which velocity is direction and speed. If it changes, that's actually acceleration. So it could go from no threat to potential threat to a definite threat. Or if you actually have a collision where you have a gravitational field like Jupiter that has a lot of effect on it, you can take one thing and break it into 9. Or you can take one thing and split it into 2. Or you can have, when there's a collision, you can have one thing becoming 2 or a handful of things. Nothing is ever static in space. When you think you've got a good bead on that orbit, something can come in and change it. but we've created perturbations ourselves. NASA's DART mission, the Double Asteroid Redirection Target, no, task, forget what the T stands for. NASA sent a probe to Dimorphos, which was an asteroid orbiting another asteroid. And we didn't know that Dimorphos was a rubble pile until we got there and started taking pictures of it. But by then it's too late, and we were already on impact trajectory. You see this shotgun blast coming off of Dimorphos, which changed its orbit, but that stuff went places. And what we found out was, like Earth has meteor showers, well, Mars now has a brand new meteor shower courtesy of humans. And also, a few of those are larger objects, not ending objects, but they're new impacting asteroids for the planet Mars. Mankind created new impactors for the planet Mars. Sorry about that, Mars. Even for Earth, they created new, what they call moonlets. These are short duration Earth orbiting objects, asteroids, and they will be in a not long-term stable orbit around the Earth, and then they'll fly off towards the sun. But be careful when you want to destroy something, because the stuff's going to go everywhere. So I have some comparative pictures here of rubble piles. So we sent the sampler to Bennu. And if you look at the top picture, Bennu is a lot bigger grains, a lot more tightly packed together. But that's where we got that sample from, where when we hit it with the sampling instrument, it actually scooped up a lot more material than we had originally envisioned. And it actually filled up the outer part of the chamber to the point where we had to sort of shake it a bit to get it to close, because it was so much more filled than we thought. And Dimorphos, which is the one we did impact, you can see that there's a lot more dirt between the rock particles. So it was a lot easier to create that blast of material off of it. And if you remember Shoemaker-Levy 9 at Jupiter, nothing actually hit it to break it up. It was just these shearing forces as it came in towards Jupiter, that Jupiter's gravity accelerated the front of the asteroid more so than the back of the asteroid and pulled it apart. That can happen. So if something is, let's say, a rubble pile or a few chunks, and it heads towards Earth, it might not originally have been something that was going to hit Earth, but the gravity of Earth pulled it apart. And now, instead of having one thing hitting Earth where we knew it was going to hit, at the last minute, we have multiple things. Some may hit Earth, some may not hit Earth, but now we've got to recalculate all those trajectories. Let's say it's not a rubble pile. It's a little denser than that, like a comet. If it's a fairly new comet, there'll be a lot of ice in it. If it's an old recurring comet, it'll have a lot of fissures where the ice is diminished by each orbit producing the tail. And if you have a sufficient quantity of fissures, and this thing does come into Earth gravity field, it can actually fracture like crunchy based upon those fissures that water ice used to be in. But they're talking about this latest one they found late last year as being more solid, like stone, like a flying chunk of a mountain. And they're getting at this because they looked at the light curve. You know, they watched the albedo, the reflectivity of this thing, and it has a rotation pattern of less than 1 hour. I forget the exact number of minutes, but it's less than 1 hour. And they said that if it really was spinning that fast and it's this size, then it probably isn't a rubble pile, because the rubble pile would have sort of thrown itself apart due to the rotational forces. So they're predicting this thing to be stone. They're looking at the reflectivity and saying it's not quite reflective enough to be metallic or stony metallic, giant rock. But its shape will make a difference too. If it's large enough, there's this thing called hydrostatic equilibrium, where the gravity of the object itself will crush it into being more spherical. If it's spherical, as it comes into the atmosphere, that presents a larger surface area for the atmosphere to put friction as well as pressure, shock pressure, to break it up prior to ground impact. But let's say it's not large enough to be round. Let's say it's an oddball shape, kind of tumbly and spiky. That's going to hopefully make it more susceptible to breaking up during reentry. But let's say it's more spear-shaped, rod-shaped, Some say turd shaped, but it's elongated. If it enters the atmosphere sort of narrow surface area first, that won't be enough atmospheric interaction to slow it down sufficiently and maybe not even break it up. There was a U.S. Department of Defense effort called Rods from Gods, where we weren't going to put any nuclear missiles in orbit. We were just going to put giant metallic telegraph poles, and we would just eject those down to the Earth. So instead of using like nuclear missiles to hit a target of an adversary, we would just send these things re-entering at 20,000 miles an hour, and they were giant, dense metallic rods, kind of like this thing would be. Just because it's not that big depends upon what its shape is, how fast it's entering, and the incoming direction. If it's coming in from the outer part of the solar system, we have sort of the sun at our back, and therefore the sun will illuminate it, and we can see it moving across the sky. But let's say the sun's in front of us and it's coming in from the sun. We think of the sun as being this disk that's about a half a degree across. But the actual illumination, the part that you find difficult to see around and through, is a few degrees across, not a half a degree. So that area is blotted out. So if it's coming in from that area, like whipping around the sun, we won't see it until it gets much closer to Earth. Or if it's out farther from the sun than that, and it's already come between the sun and us, then the sun is at its back. So it's like looking at the moon during a new moon. The sun's on the back side of it, making it harder to see. So that's why we should analyze these things as they're going past us. Don't count anything as being out of bound. If you see something moving, go ahead and track its orbit, even though at first blush you go, well, that's going by us. It's not going to hit us. It could go around the sun, come in from the sun, and hit you. Track everything, not just the stuff that's an imminent threat. But the two places that we aren't looking is the North and South Pole. There is no observatory at the North Pole because most of the time the North Pole is Arctic Ocean water. So unless we had an observatory on a ship, you're not looking directly up from the North Pole. And remember, the Earth is tilted 20 some odd degrees. At the South Pole, we do have observatories, but there's not a lot of optical observing down there. It's a lot of neutrino and radio observing and infrared. So the observatories at the South Pole aren't at the South Pole. They're at the outer edge of the Antarctic continent. So not a lot of observing ability down there to track things. So let's say we've decided it's going to impact the Earth. That's a for sure. Let's just make that a given at this point. Where is it going to impact? And depending upon where it impacts, that will be either not a big problem, a very big problem, or a potentially Earth hazardous problem. So let's say it lands, it's going to land in a body of water. If it's small enough and it lands in an ocean or a lake or a river, no biggie, it'll make a splash. If it's big, it can make lots of waves that anything along the shoreline might get decimated. But let's say it lands in shallow water. Instead of blowing up water, it's going to be blowing up essentially mud, the marsh, and that's a lot denser when it hits something. So that's if it hits water. Let's say it hits land. If it just hits the land itself, if you look at the moon, you can see that when things hit the moon, it actually heats up the rock of the moon, makes it molten, and then makes kind of like lava where there was no volcano. Or if it actually hits an area, it can throw up enough debris, it can set off volcanic action, which produces ash, which produces what they call a nuclear winter. And the sun gets blocked out, and that changes agriculture and all kinds of stuff, bad stuff happens, even if it doesn't strike you directly. Let's say it hits an uninhabited area. Let's say Siberia, up at the northern tundra. Well, there's still a few people up there. There's animals up there and such, but it's less impact to populated areas, to major areas, which is kind of a good thing. Bad for them up there, but kind of a good thing. But the effects can be extended. So if this thing does happen to trigger a volcanic response and a lot of ash comes up as a result of it, that ash cloud can blow to the west over a populated area. We saw this with Chernobyl. Chernobyl produced a lot of material into the air, and then the wind carried it to the west, and it started going over other countries and dropping radioactive ash. So you can have an impact in one place that will affect somewhere that was totally unrelated to the actual impact. Kinds of areas it could hit is lightly inhabited, reduced destruction possibility, but it could affect, let's say, farming, agricultural areas, and there could be follow-on effects from the reduction in agricultural output. Or it could hit densely populated major areas. It could be major loss of life, major loss of buildings and infrastructure. Let's say it hits a technology center or a financial center. Hopefully you have backups. Let's say it hits a large population center, but we see it coming in advance. We have to have a massive refugee migration effort. People that are coming from an area that was densely populated to an area that's lightly populated may not have the infrastructure in place to easily support that community coming in and dominating the total population of that area. And if we lose water supplies or farming or such, then even that migration can have a shortage of consumables. And we know from recent past how dire things can get when you can't get paper towels and toilet paper. So imagine if you can't get food and water. So how do we deal with this stuff? Remember, it's a planetary defense goal. The first thing we want to do is, if we determine it's an extinction level event, it's a large amount of preparation and hope for the best. If it's going to be some loss of life, but not an extinction level event, then we might want to migrate things if we see it coming soon enough, or create new infrastructure to replace the infrastructure that's going to get hit. And also understand what the follow-on effects are going to be. And remember, it's not like the movies. We're not going to send some nukes up and blow this thing, whatever it is, into dust. That's not how things work. We need to determine what's the likelihood, where it's going to hit, what the atmospheric impacts are going to be. Is there anything we can do? Ultimately, the best approach is not try and blow it up. But if that's all you've got at the last minute, you might suppress things or reduce the spot impact if you did try and blow something up or blow it into multiple pieces. That's kind of a last resort. The most effective deterrent is change its orbit while it's out in deep space. It's easier to do it that way. But how do you change the orbit of something? All you're really doing is changing something called the velocity. Remember, velocity is speed and angle. You want to change the instantaneous velocity by some amount, by a delta, a change. So you'll hear a lot of discussion of, we need to change the delta V, delta being the Greek letter and V being velocity, change in velocity. We don't need to nuke it. We don't need to attempt to vaporize it. Besides that, if something's big enough that it's a threat to the Earth, all the nukes on the planet will likely be insufficient to vaporize it. If it's a rubble pile and we nuke it, it's just going to create a shotgun scatter blast, and it's going to fall down that way or recoalesce. But what you can do is you can push it or pull it using some amount of force at some angle. But to achieve the amount of alteration needed to make a difference, you may have to deploy whatever force you're doing for a long period of time. So much like solar wind is a small amount over a long time, you may have to technologically be creative and come up with a force that will work for a long period of time. Or if you're using, I'm going to send bombs down to blow surface material off, you may have to do that a number of times to get the desired course correction. And even if you change it now, a future orbit may come by where you need to hit it again, so to speak. And let's say you had one thing and then you went to change its orbit, and now you've got two things, and one thing's still coming at the Earth, and the other is kind of like, I'm going to circle around the sun, hit the Earth from the other side. So now you've got two things in space that are in different places. Now you need two of these things to go hit both of them after you've already expended your first shot to hit, and it broke into two. So you have to think about, is it just one thing or is it multiple things? And are the multiple things the result of the first attempt, or the multiple things just because there's multiple things coming in? Let's say Jupiter broke up one object into 10. Now you've got 10 moving apart separate things you've got to hit. So let's think of a source of delta V for pull. We're going to pull on this thing that's heading towards Earth. So if we have a large mass and we put it not into orbit around it, but we put it like off to one side of it, the gravity of this mass that we put there, we keep it in that spot, it's going to slowly tug on it to change its orbit. But how much do we have to put up there? We may not have sufficient rocket horsepower to put the total sizable mass up there that we need. We may have to put up like multiple things and then attach them to one another once they get there and then tug on it. We may have to leave it up there tugging for a long time because it's a small amount of tug for a large object. We're going to need to communicate with that thing to correct its course. And if it goes behind the sun or behind Jupiter, we're going to have a communications loss for months. If we put it up there, remember, it's not orbiting, it's no free ride. It's going to be constantly using fuel to pull on the thing that we want to change its orbit. So it's going to need a lot of fuel for that propulsion. And if we're sending up a high mass, need even more fuel to constantly be tugging on it. And even ion propulsion has a fixed size tank of fuel. Remember that with the probe that wound up at Ceres because they wound up out of fuel for continuing to go elsewhere, and it's now in kind of permanent orbit about Ceres. And if we have only a sufficient amount of gravity that we can go up there and pull with, and it runs out of fuel or we didn't have enough mass, when we find out it's insufficient or we need to do it repeatedly because this thing is rotating or there's other perturbations we have to counter, then will we have enough time to put more mass up there or put new mass up there? And that's for just one object. What if we had to deal with a couple of objects and they're spread out? So instead of pulling, let's push on it. We want to blow something up. Let's blow something up. Okay, so we're going to send something up there and it's going to explode near it to push it away. An explosion is a force. The force has a certain size, maybe even large, but it's a short duration. So if it's not sufficient, then we have to send up something either as big or bigger and do it multiple times to achieve the desired course correction. Even if we blow a lot of stuff up, we may not have enough force to push on the front of it to slow it down. Maybe we should blow up behind it to speed it up to let it get by the Earth's orbit before Earth shows up. So not just slowing down, but speeding up is an alternative. Or we could blow up on the side of it to push its orbit out, to widen its orbit, which would change its orbital velocity. And maybe that's how we at least postpone it for a while. But the idea here is it's not a one-time thing. You may have to hit it multiple times over time. And if there's multiple objects, you have to hit multiple objects. And if the object is tumbling, you may have to hit it several times before you can get the course corrected as you need. So on Star Trek Next Generation, Q, they were trying to alter the course of a deep space object that was about to create an extinction level event for a planet. And he said, it's simple, just change the gravitational constant of the universe. And then they had to explain to him, we don't have the technology to do that. Oh, well, why don't you just change the mass of the object, increase it or decrease it? If you want to decrease the mass of the object, that will give you your delta V. I've seen programs where they're going to send something to an asteroid or comet. It's going to drill down into the surface. It's going to gather material from it, and then it's going to eject that material out into space. So not only are you removing the mass, which changes its delta V, but you're also ejecting material. So that's like a little rocket engine. So F equals ma, force equals mass times acceleration. So you get two things going on there. And that works great as long as the object's not rotating. And as long as you don't change the object too much. Think about it this way. If you send one mass ejector to drill and eject, and you go, great, and then the object starts to rotate, now you can only eject more mass every time the rotation puts it in the right direction. So you may have to drill down and then not eject until some number of hours later. But if it's spinning fast enough, now you either have to have multiple of these drillers or you have to move the position of the drillers. So the driller can't be staked into the asteroid or comet. It's got to be like a little tractor so it can move around and change. And if you're doing all that stuff, that driller and rover is going to need an energy source. And if this thing happens to be rotating, It's not always going to be in sunlight for solar panels. Could be in shadow. And then I know the next thing people will think of is nuclear power. No, don't worry about the solar panels. I know you want to blow it up or you want to send a nuclear reactor there. If your solution is incorrect and your solution to the solution is nuclear, either power or explosives, then nuclear becomes your hammer and anything else is a nail associated with it. So let's work on the original solution being better so we don't have to do the nuclear. So what if we just wanted to increase the mass instead of decreasing it? Well, how do you increase the mass of something? Well, we could go grab a small comet and put the small comet in front of its orbit and let the debris tail of the comet like hit the surface of the object we want to change the velocity on. And okay, that's great. How much did you change it by? Well, we won't know until we get there because we don't know about the mass of the debris field coming off the comet. And if you have enough technological propulsion prowess to go grab a comet and put it in front of the object you want to slow down, why don't you just slow down the original object? Why go get a comet? Or you can say, well, we'll go grab a small asteroid and we'll detonate explosive on the small asteroid to break apart the asteroid, and then its debris will fall upon the object that you want to slow down and increase the mass of the object. Once again, if you've got the technology to go grab an asteroid, blow it up to slow down the other thing, why don't you slow down the original thing you had a problem with? And the other thing is either using a comet tail or a exploded asteroid is kind of a single bullet derringer. If you find that it doesn't work, you've used the only round you had, and either you won't have the technology to do anything further, or it could take you years to go get something else to move it back in place. What if when you do increase its mass, it splits into two things and they start moving on different orbits? Where are you going to get some more bullets for your derringer? I've even heard about programs where we're going to send up a large container full of heavy debris, and we're going to spray it like dense spray paint out of one spacecraft onto the surface of this object we want to change the velocity of. And my thought is, if it's big enough to be a threat to the Earth, what technology do we have that will allow us to move that much mass into an orbit with the asteroid and then spew it with this coating? If you can do that, hell, spray it with plastic, let it hit the Earth's atmosphere, and the plastic will cause a reentry burnup of the object. The spraying doesn't make sense when you have multiple targets you have to deal with. Then I've seen the other source of push. Well, if the solar wind can push on things, then why don't we just use the sun, go put giant mirrors up there and have the sun hit this thing and either blow stuff off of it or concentrate the radiation pressure to push on it? That makes sense. But, there's still people that don't believe that the sun can push things. Took 40 years for them to figure out that ion propulsion's actually usable and practical. How long do you think it's going to take them to realize that, well, our solar sail tests work fine, but enough to move a giant comet or asteroid? No, get serious. So we'd have to move multiple large mirrors. Can we build and move the mirrors in place large enough to do this? And we might require multiple of them. And what if the object is rotating? We only want to hit the object every so often. So anything that we put out there that's got to be there for a long period of time to get the reflection to gradually slow it down, it's going to require communications. And if this thing happens to go behind the sun, it's going to be out of communication for months. If it goes behind Jupiter, we're catching it on the other side, same sort of thing. Some of these solutions aren't as simple as you think at first blush. So here's another alternative push. If the radiation pressure works, then why don't we just have Earth orbiting lasers push on it? If you don't have to send your deterrent force all the way out to the object, if you just have to put them in higher than geostationary Earth orbit, which means they're on a slow orbit, and they're solar powered, and they're a couple of megawatts apiece, and you have a couple of satellite ground stations on Earth for communicating with them, you're not using the deep space network. There's no obstructions in the way. They're going to hang overhead for a long period of time while you communicate with them. The fact that it's orbiting slowly will actually give you a longer sunlight period for the solar panels than 24 hours. It's in orbit, so not a lot of fuel for course correction. You could use ion propulsion, or keeping them at where you want them. You could use momentum wheels that we already understand fully to point it at a target and to keep it tracking on the target. You don't need to send anything out to the target. The time, the cost to do all that stuff, what could go wrong? You could have a sustained duration of the laser on the target. If it's out there beyond geostationary, there's nothing in the way. As the Earth rotates, you could have multiple of these satellites and just switch from one satellite to the next as the next satellite in line is now pointing at the object. If you need multiple satellites for redundancy, that's not a problem. We know how to put constellations of satellites in orbit. If you need, let's say, multiple targets you want to take out, having a constellation of satellites, you can do that. Also on these satellites, you can include optical or radar telescopes. So you can use them not only to deter something, but you could also use it for regular reconnaissance. So if you had a permanent staff manning these orbiting, observing, and laser satellites, now the near Earth object and the planetary hazardous object stuff, you've got the instruments for that. You don't have to like borrow from some other instrument to do it. Well, why don't we just put those lasers on the ground and shoot out into space? We can do gigawatt lasers. That may take less time to create it and deploy it because it's all on the Earth. And it doesn't require orbiting satellite communications. And you can tap into the existing power grid, put in solar fields, wind turbines, or generators, or in the future, fusion generation. But I'm not going to recommend ground-based lasers because it's a fixed location laser. You have to wait until the Earth rotates around before you can turn the laser on and hit something in that direction. It reduces your targeting flexibility. The beam would have to pass through the atmosphere. That means instead of megawatts, you need gigawatts. That increases the cost. And as it passes through the atmosphere, the beam is going to be diverged. It's going to be distorted by the atmosphere. If you've got one place where the laser is and the target is over the horizon, you're going to be firing this gigawatt laser through the atmosphere over other countries and heating up their atmosphere. How are they going to feel about that? If it's a beam that comes up from the Earth, there's a big thing in the way called the moon. What if the object you need to keep the beam on goes behind the moon? What if it goes behind the sun? You need enough opportunity to deter its orbit. So not only should you have them in orbit of the Earth, high geostationary, how about putting them at the couple of the Lagrange points so you can catch things before and after the sun, before and after the moon, or maybe put something on the far side of the moon. So it's a multi-station aspect of this. Now, is it going to cost us billions of dollars to do this? Yes, but all the satellites can be pretty much the same. So once you've designed it, cookie cutter them. And I think we can do that because we already have constellation satellite systems in orbit. But since they're satellites and they're fixed fuel supply, even if they're ion propulsion, about every 5 years, you're going to need to replace these satellites because they're going to run out of fuel, just like Gaia, the probe that's out at L2, recently ran low enough on fuel that it ended its scientific mission, and they're just getting data from it now, and they'll eventually kick it into like an L5 or an L4 orbit around the sun with the Earth. But by having these out at these Lagrange points, we can also catch things coming towards the Earth from the sun. So in summary, there's stuff out there always impacting the Earth all the time. Most of it is just ash or dust from either bolides that are visible or from invisible burnups that happen out over unpopulated areas or the ocean and we never see them. Larger objects do have a potential for greater adverse effects. And depending upon the where it lands, the angle, the velocity, and the composition of the object, that determines what's the adverse nature of the object. And the largest of them produce extinction level events. And if you don't think these things are possible, ask the dinosaurs. We're going to need to find a way to assign people to do this on a 24/7 forever, to look for these things and come up with ways to defend the planet from it. The NASA and Department of Defense do have planetary defense departments within the larger organizations. But a lot of that focus is on, hey, we found one, let's nuke it. No, please don't. It's not going to be enough. And no. Now, let's say we did actually create a defense network, and it did defend the planet once, and we were successful. And then for a number of additional decades, we never find anything we have to defend ourselves against. Well, that means after maybe a couple of generations, people will forget why we put it there in place to begin with, and maybe we don't need it anymore. So if we're not successful defending the planet, or if we don't notice it and don't have the technology to defend us, then something unsuccessful will happen, and we'll lose some major cities. We'll have some unexpected migration problems. And if we have something like that, that will be the trick me once, shame on you, trick me twice, shame on me. If we learn from that first unexpected, undefensible event, and then we create a defense, now we're going to spend however much money it costs to create something that we might never test for 100 years. In which case, instead of a couple of generations, after maybe 4 generations, we once again go, we built all this for nothing, spent all this money for nothing. And so we'll become forgetful as a species, and our patience will grow, and we'll say, well, we built that thing for billions of dollars. Do we really still need to keep funding it? And they'll want to redirect money away from it. And then's when something will come in. It's a complicated situation. And then I've got links to historical things, missions, and such. Okay, so how many had heard of this asteroid that's going to be headed our way, and we won't know about it until 2028?
Yeah.
Did you make the connection between why 2028 and then why 2032?
No.
That's the orbital period. So every 4 years it intersects with the Earth's orbit, and every year the Earth goes around the sun. So every 4 years, it's a possibility of the 2 orbits to intersect. Intersect by
what's the diameter of this thing?
I think it's less than a kilometer. I remember it being less than a kilometer. So it's probably too big to burn up in the atmosphere. It might fracture in the atmosphere and become, a number of things hitting the surface. There's an arc that takes it from Central America around Panama, over the Atlantic Ocean, over Africa, over sort of the southern part of India, not quite into China, more like it ends about Tibet. So that's the current predicted path. But they're going back and looking through the records. It's good when we have a program like a Hubble or a Sophia or a Gaia to retain those records long after the mission is over. Realizing that, okay, if we saw this thing in 2024 and we've got a feeling that it's a 4-year orbital period, we can see it again and get a better judgment in 2028 to know what's going to happen in 2032. They said, well, what about 2020? If this thing has a 4-year period, can't we get data from all of our various observatories of that part of the sky from the year 2020 and see if we see it then? The verdict is out at the moment. They are going back and looking at every mission that occurred where there was observing done in 2020 about the same time of the year over a window of opportunity to see if in the predicted area of space, do they detect this thing? Maybe they will. If they will, now they have a better orbital path. If they don't detect it at all, then it might not have been there originally and something deflected it. A perturbation happened. It flew past Jupiter, or it flew too close to the sun and its orbit got changed. Now we have no clue where it was before 2024. There's a lot of analysis that has to go on. Right now, it's at a 2.3% probability of hitting the Earth along this red line path. 2.3%, as we get more observations, the number will climb. the number might get as high as like 80 or 90% probability of hitting the Earth. And then we see that 2028 orbit and we go, phew, no. And that 80+% will just drop off to like 0%, 1%, something like that.
Yeah.
Just remember, we on a regular basis, a couple of times a year, discover asteroids that have already gone past the Earth in the Earth's orbit because they were coming in out of the sun and we couldn't see them. We go, what was that? And we see it after it's already gone by. And then we reverse calculate the orbit and find out, oh, that went through the upper part of the Earth's atmosphere lower than geostationary orbits, sort of in the Van Allen belt region. Luckily, there's not a lot of satellites there to hit. There's stuff moving around all the time, and I think we need to create a defense network that works, that doesn't require us to send things out there or blow things up or have technology that maybe it'll work once, but what if you've got 2 or 3 things, or what if it breaks apart? You need a solution that works for more than that, and that's why I think that a space-based observation and megawatt class laser system, not to vaporize the target, but just push on it. Probably going to be long-term best approach, but we shall see. Any other comments or questions? Otherwise, I'll stop recording. Hearing nothing.